Okay, so this video is going to be recapping the GCSE and AS level Equilibria content that you have done so far in order to make sure that you're happy with the green and orange sections of the progression booklet. So the first thing to have a look at is what we mean by the term dynamic equilibrium. This word dynamic indicates to us that it's something that's moving, things are changing. And in terms of dynamic equilibrium, what we mean in that sense is that we have both a forwards and a backwards reaction, which is occurring at the same time and they proceed at the same rate. Remember also that this is a symbol that we show our reaction is reversible, and so dynamic equilibrium happens when our forwards reaction is at the same rate as our backwards reaction. Because they're happening at the same rate, it means that the composition of the reaction mixture doesn't change. So there's a constant concentration of substances in the reaction mixture. Do also note that that doesn't mean what you put in at the start with doesn't then change, because you haven't yet reached equilibrium. When you start by adding substances into, say, a beaker, it takes time for that equilibrium to be established, so you might have just put in your reactants, so you won't actually have any products at that stage, and therefore your backwards reaction won't be happening to start with. However, as more products are made from the forwards reaction happening, then your backwards reaction can start to happen, and eventually the equilibrium is reached where the forwards and backwards reactions are happening at the same rate. But that doesn't happen initially, so you have an initial amount of the substances, but that will be different to the substances at equilibrium. But at equilibrium, the concentration of those substances will be constant. This dynamic equilibrium can therefore only happen in a closed system. That doesn't mean it has to be sealed, but what it does mean is that our reactants and products can't escape, as if they escape then our equilibrium has to be re-established. Also at GCSE we came across Le Chatelier's principle, and I often talk about Le Chatelier's principle behaving like a 2-year-old. Whatever you tell the 2-year-old to do, the 2-year-old will do the opposite. So whatever changes we make to the system, the equilibrium shifts to oppose that change. So the equilibrium moves to oppose a disturbance to the equilibrium and to restore the equilibrium. So often things that we talk about is temperature. So if we increase the temperature, the equilibrium is going to shift in order to decrease the temperature. So here we want to talk about our exothermic versus our endothermic. So exothermic, remember, is going to be an increase in temperature, whereas our endothermic will reduce the temperature. Exothermic, we're releasing thermal energy, so our temperature of our reaction mixture increases, whereas in endothermic we are taking in energy, and so our reaction mixture temperature decreases. So the change we make to our temperature is going to determine which reaction of the two is favoured, either the exothermic or endothermic. So if we were to increase temperature, our equilibrium is going to move to oppose this disturbance, and so it's going to act to decrease the temperature, and so endothermic is favoured. Whereas when we decrease our temperature, the equilibrium is going to move to oppose this disturbance, and so we end up with an increase in temperature. And to do that, our exothermic reaction is favoured. We also look at pressure. And here we talk about our number of molecules on each side of the reaction. And here we can link this into a different topic of our AS chemistry, and that's when you looked at the ideal gas equation. So ideal gas equation, PV equals nRT, and the crucial relationship we want to be looking at here is this link between pressure and our number of moles. So pressure is directly proportional to the number of moles. So if we were to increase our pressure, we would then need to be able to decrease that pressure by affecting our number of molecules that we have in that reaction mixture. So in order to decrease pressure, we're going to have to decrease the number of moles. So the change we're making is increasing the pressure, but the change in terms of the shift of the equilibrium is acting to decrease the number of moles, so side producing fewer moles is favoured. However, if we were to decrease the pressure, our equilibrium is going to move to oppose the disturbance and try to increase our pressure. And in order to increase pressure, we then increase our number of moles. And so to do that, the side producing more moles is favoured. And I've just noticed wrong symbol there. That is our directly proportional symbol. A useful simulation, which I'm just going to quickly insert here, which links nicely to the pressure aspect of Le Chatelier's principle. So we've got two gas syringes here, both same reaction mixture, so 2NO2 going to N2O4. So at the moment there isn't much pressure on these molecules, and we can show that increasing the pressure by moving the syringe in then changes what our reaction mixture is composed of. So you now see there are two N2O4 molecules there, and this is because as we're increasing the pressure, our equilibrium is shifting to oppose that change by favouring the reaction which produces fewer moles of substance. So there's only one N2O4 molecule for every two NO2s it takes to form that, and so that is decreasing the pressure as we are increasing it. So it's acting to oppose this change, so continuing to increase the pressure, but the reaction equilibrium shifts to oppose that change by favouring the reaction producing fewer moles. And so now we're at the highest pressure and our equilibrium is all the way over to the N2O4 side, whereas at our lowest pressure up top, we're right over onto the left side with the two NO2s, as we've decreased the pressure, and so it favours the side producing more moles in order to then increase the pressure. A simulation looking at pressure. So as I add particles into my container, I can keep my temperature constant, and I want us to focus on this pressure gauge. So as I increase my number of particles, I'm increasing the pressure, and that's because with more particles in this container, you're having more collisions with the container, more collisions with the other particles, and so you're exerting a greater force on the area and therefore increasing the pressure. If I were to reduce my number of particles, you can now see the pressure dropping as there's less of a force being exerted on the container and therefore a lower pressure. The other thing that we can talk about is our amounts of our substances. So if we were to remove one of our products or remove one of our reactants, then our equilibrium is going to shift in order to increase the amount of what we've been removing. So removal of product, equilibrium moves to oppose this disturbance and therefore increase amount of products produced. So if you had two products that were produced and you only removed one, your reaction's still going to favour the products, and therefore the one that you haven't actually removed, you're going to have lots of that left in there. Whereas if you were to remove reactants, you would increase, the equilibrium would move to increase the amount of reactants. So here our forwards is favoured, whereas here our backwards is favoured. One thing I want to point out as well with pressure is that sometimes the number of moles on each side is the same, and therefore pressure is not going to actually have an effect on that reaction, as both sides would produce the same number of moles. So any change in pressure isn't going to affect which reaction is favoured, as they're both producing the same number of moles, so there's no winner in that sense. Catalysts. So adding a catalyst, we know that lowers the activation energy of a reaction, allowing our rate of reaction to increase. However, this is going to affect both the forwards and backwards reactions the same, as they both have that same energy level to reach before progressing, whether they're going one way or the other. So they've still got to get to the same energy level. So whilst adding a catalyst lowers that energy level, it does it for both sides of the reaction, and so it has an equal effect to both of them. So our equilibrium position doesn't change, however we would reach our equilibrium faster. So catalysts allow equilibrium to be reached faster, but no change in position. And that's because it affects both of those rates equally. So turning more now to our AS side of this topic, so looking at an generic equilibrium where we've got our reactants and our products forwards and backwards. So at equilibrium, we know that our concentrations of each of these substances is constant, and that means that the ratio of these substances is going to be constant. So what we can do is have an expression for our concentrations at equilibrium, so the equilibrium constant. Which is abbreviated Kc. Now, at AS we didn't really mind why this C was here, we just knew that this was an equilibrium constant. But what's going to become important in this bridge to A2 is that this is due to it being in terms of concentration. So that's what that C stands for, is that it's in terms of the concentrations. So our Kc is always written in terms of our concentrations of our products divided by our concentration of our reactants. So it's that ratio that gives us that equilibrium constant. Notice I haven't given any units, as our Kc units vary depending on the moles of different substances. Sometimes it won't have any units if we have the same number of moles on each side of the equation, then our concentration units cancel. But for this generic expression, our stoichiometric coefficients are used as indices. So capital C in square brackets, this shows the concentration of that substance C, and then that little c is your stoichiometric coefficient, so telling you the ratio of the number of molecules in that equilibrium. And then concentration of D divided by A and B. So this equilibrium constant will tell us the composition of the equilibrium mixture and the position of this equilibrium constant. Because if we have a Kc that's greater than 1, this tells us that our products is greater than our reactants. And therefore this shows us that our forwards reaction is being favoured. This perhaps becomes clearer when you think about this in terms of a random number that meets this. So if we use the example of, 12, if Kc is equal to 12, our ratio between products to reactants is then 12 to 1. So it doesn't matter whether these numbers are right or not, but what it shows is that the products is greater than the reactants. This helps more so when we're talking about Kc's less than 1, as here if we have Kc 0.25, then what we're saying here is that it's 0.25 to 1, and then here we can see that actually our products is less than our reactants. And if our products is less than our reactants, that means our backwards reaction must then be favoured. So our equilibrium constant only changes if temperature changes. So Kc is constant at a constant temperature. No other variables affect Kc, only temperature. And so in order to determine how Kc changes with temperature, we need to think about what Le Chatelier's principle taught us about changing temperature. So with an exothermic reaction, if we were to increase temperature, our equilibrium would want to decrease, and so our endothermic reaction is favoured, and so therefore our Kc would decrease. Because if our forwards reaction is exothermic, our backwards reaction is endothermic, therefore our reactants has become more favoured than our products, and so our Kc value must be decreasing. So oppositely, if our forwards reaction is endothermic, if we were to increase temperature, again equilibrium shifts to decrease the temperature change, and so endothermic is favoured. However, now because our forwards reaction is endothermic, it means that our products are being favoured over our reactants, and therefore our Kc would increase. If we were decreasing the temperature, we therefore know that opposite one would be favoured, and therefore the opposite effect to Kc would happen. Okay, so just to recap what we have covered. So what is a dynamic equilibrium, and what is a closed system, what does Le Chatelier's principle state, how does changing temperature affect the position of equilibrium, how does pressure changes affect the position of equilibrium. What happens if one of the substances is removed, and what effect do catalysts have? What is an equilibrium constant? What are the units? For Kc, what does the size of Kc tell us? And how is Kc affected by temperature?